स्टेज पर दावत देने जा रहे हैं जो इस महफिल की शान है। So let us welcome all the dignitaries with a big round of applause. To begin this event with the blessings of the Almighty, let us have the recitation of the Holy Quran. Now I request our BSc student Zaid to kindly come forward for the recitation.
أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. وقضى ربك ألا تعبدوا إلا إياه وبالوالدين إحسانا إما يبلغن عندك الكبر أحدهما أو كلاهما فلا تقل لهما أف ولا تنهرهما وقل لهما قولا كريما واخفض لهما جناح الذل من الرحمة وقل رب ارحمهما كما ربياني صغيرا ربكم أعلم بما في نفوسكم إن تكونوا صالحين فإنه كان للأوابين غفورا صدق الله العظيم. Your Lord has decreed that you worship none but Him and do good to parents. If any one of them or both of them reach old age, do not say to them, "Uff," a word of or expression of anger or contempt, and do not scold them and address them with respectful words and submit yourself before them in humility out of compassion and say, "My Lord, be merciful to them as they have brought me up in my childhood." Give the relative his right and the needy and the wayfarer, and do not squander recklessly. Jazak.
Jazakallah for the soulful recitation. I, Dr. Habib Rahman, once again feel a moment of immense honor and intellectual pride to welcome you all to the inaugural ceremony of the VO4Edu workshop, a journey where astronomy, data science, AI, and education converge to explore the universe of knowledge. As such, we gratefully acknowledge the financial support from IUCA Pune under BRICS Astronomy, and this event is going to jointly organized by the Department of Mathematics and Physics under School of Sciences, Maulana Azad National Urdu University, Hyderabad. To instill the spirit and ethos of our university, जैसा कि हर इदारा सिर्फ इमारतों का मजमू नहीं होता बल्कि एक रूह होती है, एक पहचान होती है, और मानव की यही पहचान है उसका तराना। अब हम मानव तराना वीडियो के जरिए पेश कर रहे हैं। बिफोर दैट आई वुड लाइक टू से दिस तराना हैज बीन ब्यूटिफुली रिटन बाय our Honorable Vice Chancellor, Professor Padma Shri, Professor Syed Ainul Hasan Sir, which reflects the vision, philosophy, and soul of this institution. So we shall now have the Manu Tarana. Sound.
सफल यहाँ से करे आसमान का ilmu kamalu fadlu syiaru syuhur takdir hai nawaznya tur takdir biltamne hali sabab sare jahan ka आजाद कर सिवा की है ये भी जुस्तजू सब मौसलों में खाते चलो दरमियान का ये आगे शहर गर्वो जुनूब से हो शर्को शुमाल से साहिल पर वो ख्याल मिला दो ख्याल से चर्चा तुम्हें हिंदुस्तान का आगे शहर सदा बहार बस्ती बस्ती रहे मिलकर हुआ करो कि ये भी हरी रहे सारे सरों पे किसी साए डोली का मेरी शहर आओ सफल यहाँ से करें आसमान का मेरी शहर
before we proceed further, let us take a moment to express our gratitude. As we know, gratitude is the memory of the heart, and gratitude is the most elegant expression of respect. So, to formally welcome our esteemed dignitaries with the mementos symbolizing growth and sustainability, may I humbly request our Honorable Vice Chancellor Padma Shri Professor Syed Ainul Hassan sir to kindly present a token of appreciation to our today's esteemed chief guest and keynote speaker, Professor Ajit Kembhavi, Professor Emeritus from IUCA Pune. So kindly accept this memento as a token of our heartfelt gratitude for your gracious presence. May I now request Professor H. Alimbasha, our Dean, School of Sciences, to kindly present a token of appreciation to our esteemed Honorable Vice Chancellor Padma Shri Professor Syed Ainul Hassan sir. Sir, kindly accept this moment as a token of our deep respect and gratitude. Now I request Head Department of Math Physics, Professor Rafiq Abu Turab sir, to kindly present a token of appreciation to our Dean. Sir, please accept this memento as a symbol of our appreciation. May I now request Dr. Priya Hassan, convener of this workshop, to kindly present a token of appreciation to our Head Department of Physics, Professor Rafiq Abu Turab sir. Sir, kindly accept this token as a gratitude. Now I request our MSc Physics student Saklain to present a token of appreciation to our convener of the workshop, Dr. Priya Hassan. Madam, please accept this memento. It represents immense gratitude of the entire organizing committee and the participants. Moving further, a warm welcome creates the foundation of meaningful collaboration, for which we now invite our Dean, School of Sciences, Professor H. Alimbasha sir, to deliver the welcome address on behalf of the School of Sciences.
Bismillahirrahmanirrahim. Assalamu alaikum wa khush amdeed. On behalf of School of Sciences, I extend a very warm welcome to our respectable Padma Shri Professor Syed Ainul Hassan sir, Vice Chancellor of this university, distinguished chief guest of today's session, Professor Ajit Kembhavi, for gracing this workshop as keynote speaker on AI basics and astronomy applications. Thank you, sir. My colleagues, Professor Muhammad Rafiq Abu Turab, Section Head Physics, Professor Syed Ainul Hassan, Professor Syed Najmul Hassan, sir, Officiating Head, Department of Mathematics, and Convener Dr. Priya Hassan for organizing this kind of international workshop. Dear colleagues, students, and participants in a hybrid mode, I wish to extend a warm welcome to all the participants of this three-day workshop jointly organized by the Department of Mathematics and Physics section at MANU in collaboration and sponsored by IUCA Pune, that is Inter-University Center for Astronomy and Astrophysics. I wish to inform that Maulana Azad National Urdu University is a central university established by an Act of Parliament in the year 1998 with A+ grade, now in the third cycle of NAC ranking. Manu started his journey with distance education programs in 1998 and consolidated its regular academic and research programs from 2004. At present, the university is having 8 schools with 24 departments and more than 100 programs from certificate to research level. Further, to meet the rising aspiration of youth in general and Urdu-speaking community in specific, the university is making considerable progress in all fronts of academics, research, and governance with a specific vision, mission, and objectives under the able guidance of our dynamic leader, Professor Syed Ainul Hassan, sir. Thank you, sir, for your leadership. Now, Manu has created the School of Sciences in the year 2006 with a small program diploma in information technology to establish a unique educational program of study different from human-centered subjects, considering the importance of science education in development of nation in many areas. The school has established the Department of Mathematics in the year 2011 and later on botany, chemistry, physics, and zoology in the year 2014 and allied health department in the year 2019. At present, the School of Sciences at this university is a growing academic division dedicated to scientific education and research. It offers undergraduate programs with dual major subjects as per National Education Policy 2020. PG and PhD programs in botany, chemistry, mathematics, physics, zoology, and allied health program streams. The school has also added PhD program in sponsored or self-finance mode for working professionals. Similarly, 2 more PG programs will be added from next academic year as MSc Bioinformatics and MSc Industrial Chemistry from Botany and Chemistry section respectively. Sir, so far 34 PhD degrees have been awarded from this school in the last 10 years. So I wish a very grand success to this international workshop and hope that science learners will be very much benefited from this workshop. Once again, a warm welcome and all the very best for the upcoming sessions in coming 3 days from today to 25th of March 2026. Thank you once again, Jai Hind.
Thank you so much, sir, for setting such a thoughtful tone. Continuing the felicitation ceremony, may I humbly request our Honorable Vice Chancellor, Professor Syed Ainul Hassan sir, to kindly present a token of appreciation to Professor Ranjan Gupta from Ayurka Pune.
नहीं
Similarly, now I humbly request our Honorable Vice Chancellor to kindly present a token of appreciation to Professor D. Alexi.
That's it. What is going
Okay, moving forward, now I humbly request our Honorable VC sir to kindly present a token of appreciation to Professor S. More. Thank you so much, sir. In the next segment, to begin with, साइंस हमेशा से इंसानी तरक्की का मरकज रही है. फिजिक्स एंड मैथमेटिक्स दोनों मिलकर कायनात को समझने की जुबान बनाते हैं. एंड मैथमेटिक्स इज द लैंग्वेज इन विच द यूनिवर्स is written. So now I kindly request Head Department of Physics, Professor Rafiq Abu Turab sir, to deliver a welcome note and give a brief introduction about the physics section and the Department of Mathematics. Over to you, sir.
Very good morning to one and all. It is my pleasure to welcome all of you to the 3 days virtual observatory for education observatory training workshop. This workshop aims to introduce educators, researchers, and students to the educational potential of virtual observatories, empowering them to integrate real-world astronomical data into teaching and learning. I welcome Vice Chancellor Padam Shri Professor Sayyid Ainul Hasan Sahib, Chief Guest Professor Ajit Kembhavi, Professor Emeritus Ayuka, Pune, Dean School of Sciences Professor H. Alim Basha, Convener Dr. Priya Hassan, and Co-Convener Professor Najmul Hassan Sahib, colleagues and participants. The Department of Physics was established in 2014, and the first batch of undergraduate courses started in the same year. Since its inception, the department offers BSc, MPC, and BSc MPCS programs with an intake of 40 students per program. The department has been following the choice-based credit system, CBCS, in accordance with UGC guidelines since 2016. The PhD program was started in the academic session 2018-19. The MSc program was launched in the academic session 2023-24 with an intake of 20 students. The department conducts a 4-year dual major BSc honors or research with combinations physics, mathematics, physics, chemistry, and physics, computer science with an intake of 20 students per combination. The curriculum of undergraduate and postgraduate program is in alignment with National Education Policy 2020 and UGC Quality Mandate for Higher Education Institutions 2021. The department is two well-equipped laboratories and offers a vibrant PhD program with research opportunities in cutting-edge areas of physics, including solid-state physics, atmospheric physics, theoretical physics, astronomy, material science, and applied optics. Students are encouraged to undertake projects and dissertations to deepen their academic understanding and research skills. To further enrich their learning experience, the department regularly organizes a variety of academic activities, including extension lectures, seminars, workshops, national and international conferences. The department has experienced faculty members who are making significant contributions in diverse area of physics. The department is committed to fostering scientific curiosity and excellence among its students, equipping them for successful careers in academia, research, and industry. The Department of Mathematics was established in 2011, and the first batch of postgraduate courses started in the same year with an intake of 30 students. The BSc program was launched in the academic session 2014-15. The PhD program was started in the academic session 2015 and 16. The department conducts a 4-year dual major BSc honors research with combinations mathematics physics, mathematics chemistry, and mathematics computer science with an intake of 20 students per combination. The faculty has diverse research interest, namely wavelet and its applications, algebra, analysis, fluid mechanics, celestial mechanics, and dynamical astronomy. Students in the department come from different parts of the country, which makes the teaching and learning environment very rich. The aim of department is to sharpen students' rational and mathematical skills, expose them to varied possibilities of applications of mathematics to different branches of science, engineering, and industry. Wishing you all successful and intellectually rewarding workshop. Thank you all for joining us.
थैंक यू सर, थैंक यू सो मच। हर सक्सेसफुल प्रोग्राम के पीछे एक सोच, एक मेहनत और एक विजन होता है। नाउ आई काइंडली रिक्वेस्ट convener of the workshop, Dr. Priya Hassan ma'am, to brief us about the workshop and to brief us about the objectives and outline of the workshop.
Yeah, thank you, Habib. So, hello everyone and welcome to the workshop. We have a lot of outside participants and welcome to all of you all. I'm sorry for a few inconveniences you all had yesterday, but let's see. So this workshop is actually happening in a hybrid mode. We have almost 600 applicants, and since we couldn't accommodate everybody, the rest is happening online. So you'll have been also shared the Zoom and the YouTube links so that you can see that, and even later on that will be available. Yeah. So the basic purpose of this workshop is Professor Ajit Kembhavi. I did my postdoc under him, and he was basically the person who led the Virtual Observatory India program. He has been leading it for many, many years. And this is kind of in continuation to the work he's doing, which is basically virtual observatory for education. Okay. So what is the virtual observatory? The virtual observatory is basically a collection of interoperating data archives and software tools which utilize the internet to form a scientific research environment in which research programs can be conducted. So in short, it's basically an infrastructure in astronomy astrophysics because we have so much of available data now. So the ideal work would be is that even if you have your own telescope, you do have to couple your results with results from other telescopes, which is available online, and they've been integrated using the virtual observatory. So the purpose of the workshop is basically to expose students to virtual observatory. How do you use astronomy data archives to study specific science cases? So we are going to cover science cases of this workshop ranging from exoplanets to stars, to galaxies, to cosmology, to stellar spectra, to all kinds of things using machine learning as well as other tools. So that's the basic purpose of the workshop. It's a hands-on workshop where that's why we've kept it in this computer lab. If you do not have a laptop, you're most welcome to choose your favorite station and sit down and work on the computers here, or you use your own laptop. And we hope that it becomes an interactive session. There'd be lots of hands-on activities. So the ideal thing is if you can work out the hands-on activities. You'll have the files with you. Most of the people are giving you Jupyter notebooks. So if you have problems, you can always run them later on, right? So I do hope that this would be a good initiation to good science programs, science cases in astronomy and astrophysics. I would also like to mention to our welcome guests that the little presents that you got, instead of mementos, we opted for books. And these books are basically publications of our university. We have a Deccan Studies Center, and the books you all have been gifted are publications from ours. So this is to let you know what kind of work is being done over here in Deccan history. And once again, welcome to everyone. Thank you.
Thank you, ma'am. Thank you for your message. I now request Professor Syed Najmul Hassan sir, co-convener of this workshop, to introduce our today's chief guest and a keynote speaker.
Good morning, respected dignitaries on the dais and participants. It gives me great pleasure to introduce Professor Ajit Kembhavi. He's the founder member of IUCA. IUCA was founded by Professor Jayant Narlikar, the famous cosmologist of India. And Professor Kembhavi did his PhD under him in TIFR. And he was among the first ones who came to IUCA when it was established. Professor Ranjan Gupta, and so on. So he's been at IUCA and he's now emeritus professor there. Professor Kembhavi's contribution to astronomy, astrophysics, and education in general is tremendous. I'll make it very brief uh, uh, right now. He is the principal investigator of Pune Knowledge Cluster. He was elected vice president of the International Astronomical Union Office for Astronomy for Development. International Astronomical Union is the highest astronomical body in the world internationally. And he also serves as the Space Commissioner of the Department of Space India. He obtained his master's degree from Ruia College, Bombay University, and his PhD, as I mentioned, in TIFR under Professor Narlikar. Then he moved to England to work as postdoctoral fellow under Lord Martin Rees, another very big name in astronomy, in the Institute of Astronomy, Cambridge. And after his return, he joined IUCA when it was being founded. He also was the director of IUCA from 2009 to 2014. And he's served in IUCA at various levels as Dean Visitors Programs and initiated various research activity in astronomy. And for people coming from different universities, it's important for us to know that under the InflibNet project, all colleges, universities across India are getting access to internet database of a lot of scientific literature. And Professor Kembhavi was spearheading the whole action, and he's responsible for that. He is the director of IUCA for a long time, and he has participated in several international projects, including the SALT, South African Large Telescope, TMT, 30-meter telescope, Laser Interferometry Gravitational Wave Observatory, LIGO, India. These are very big projects, very prestigious projects for India, and he's been on the steering committees of almost all of these ones. And like Priya mentioned, he served as the chairman of the International Virtual Observatories India. So IVOA, International Virtual Observatory Alliance, is a alliance of many countries, about 25 or more. USA, Canada, Australia, so on, and India also plays a major part. And Professor Kembhavi was the chairperson of the Indian one. He spearheaded one, and he interacted with persistent computers and built very interesting, important tools to analyze this virtual observatory data. So the list goes on. He has won many awards and memberships. He was the Fellow of National Academy of Science, Fellow of Indian Academy of Science, former President of Astronomical Society of India, Vice President of International Astronomical Union, a former President of Indian Association of General Relativity and Gravitation, recipient of the UGC Hari Om's Vats Award for Academic Interactions with Society, Raja Raman Fellowship, former Chairman of Governing Board of Consortium for Education Communications, New Delhi, member of the Governing Counseling and Court of Indian Institute of Science, Bangalore, and the list goes on. He has written various very good books on astronomy, highlights in gravitation and cosmology, non-standard cosmology, gravitation and cosmology, and he's written books even in Marathi. So there are many more things which you'll get to know as we proceed ahead. I won't stay between you and him. And yeah, super. Thank you. We are very honored to have Professor Kembhavi with us.
Yes. We now request Professor Ajit Kembhavi, Professor Emeritus, IUCA Pune, to share his insights with a brief talk. Over to you.
Good morning. I'm very happy to be here. I should first start with an apology. This long introduction was quite unnecessary. Yes, so I always tell them do it in 2 sentences. And then I should congratulate the Honorable Vice Chancellor on the Tarana that we heard. So it was very, very nice. So I'm very glad to be here on this campus. I went out the first time I'm here, and I went out in the morning to see all the beautiful lanes and roads. And I was told that there are many campuses like this, and I think Priya, you should take me to all the campuses.
Yes, sure.
It'll be a good tour of India.
26.
Yes. So now the virtual observatory about which this program is started around the year 2000, I think. Just a couple of years after that. And I first heard about it from my friend George Jelgowski in Caltech. And then I thought India should also begin to participate in it. And then we needed the funds and we needed the computer technology. So I approached Persistent Systems. And the owner of Persistent Systems had come to Pune in the same year that I came to Pune for Ayuka. And we were running a 3-person institute and he was running a 1-person company. So then over the next years, when I thought of the VO project, that he had at the time 300 people working with him.
Yeah.
And he liked the project and he said, okay, I will give you 6 engineers free of charge. And that happened for 15 years. At the end of that time, we had about 100 people in Ayuka and he had 3,000 people. So now he has 30,000 people in the company. But we still continue to work, and which tells you how fast he is considered one of the great experts in scaling up in the country. Now, the virtual observatory itself, about we wrote about, I mean, it literally provided access to all the world's best data to anybody anywhere. So it is quite common now, somebody sitting in, let's say, Meghalaya, to early in the morning log in and work with the most recent data from any radio telescope or any X-ray observatory. And all that happened because of the back office architecture set up by the virtual observatory. So some of those things are explicit, but some of those things are implicit. So if you go to any big database and collect data from it, it will be because of the wrappers which are provided by the virtual observatory. On the Indian side, we also made a thing which is known as VO plot. We provided fabulous plotting plotting algorithms. We did a lot of data analysis and statistics. These tools were there. They are now all gone because you see that the IT technology is changing so fast that we wouldn't even be able to load that software on anything now. But the place of that has been taken up by other things in the country. And now we endlessly hear about AI. So that is going to be an important part of this workshop. So I'm very glad to be here with all of you. And my colleagues and I will be giving lectures. There's so many people who want to come from abroad, but because of various technical issues, they could not do so. Uh, but some of them will be online. And hopefully we'll have other workshops like this quite soon with all of them being present. Thank you very much.
Thank you, sir, for your enlightening address and motivating us. Now, we are indeed privileged to have with us the Honorable Vice Chancellor of Manu, Padma Shri Awardee, Professor Syed Ainul Hasan, sir, as the President of today's inaugural session. He has always been a great source of encouragement for academic initiatives and has consistently supported the promotion of science education and research. His guidance and motivation continue to inspire the academic community to actively engage in meaningful scholarly activities. May I now respectfully invite Honorable Vice Chancellor and Padma Shri Awardee Professor Syed Ainul Hasan sir to deliver the presidential address. Thank you.
Well, in the name of the one who bestowed life and wisdom upon us, Honorable Chief Guest of this morning, Professor Ajit Kembhavi, host of this conference, workshop, Dr. Alim Pasha, Dr. Priya Hassan, Professor Najmul Hassan is also here, and all colleagues, friends, girls and boys. Now, a sense of realization is coming to this university that with the help of other institutions, whether within India or outside India, university can develop high level of research and further progress in science and technology, physics and astronomy. As a matter of fact, I'm a student of language, literature, culture, philosophy, but you can't separate. And as far as national education policy is concerned, the policy suggests that it should be something called multidisciplinary. So multidisciplinary, when you call, I would recall my stay in the heart of Princeton University way back in 2007, when I was witnessing a huge department of astrophysics and very close to Einstein's laboratory. And luckily, I joined the chorus and submitted a proposal. With the help of that proposal, you see, I could submit my research work on something like cosmological advancement. You know, in this university, medium of instruction is Urdu. But it should not be underestimated. On the basis of language, we cannot decipher the very status of research and the progress made by the institution. I'm glad that we are interacting more and more these days and inviting scholars and researchers from abroad. And I'm glad to see our Russian friends sitting here. They are participating, they are somehow, exchange of ideas is more important than just organizing a conference, a workshop, and having interactions, personal interactions, and then over a cup of tea sitting and having dinner and then disbursement. Now, all these things are not taken into consideration. Rather, we should have a cluster of our academic endeavor. Now, what is happening nowadays? As a student of Persian, I studied Umar Khayyam. Rubaiyat of Umar Khayyam, Fitzgerald translated Rubaiyat, and then many other versions, every nook and corner of the world, You will find one Khayyam sitting there in a corner. So we are not here to produce Khayyams. Rather, we should go into the very essence of that Rubai, what Rubai suggested. Because even Fitzgerald, in the opening line, suggests that the astronomer poet of Persia, it seems astronomy comes first, poetry later. But it's a wonderful combination of poetry and astronomy. In the later stages, we find so much, interest developed one after another. And that's how today this university is more conducive for astronomical research. And we should understand our relationship with the cosmos. Plato, long back, 20 years back, we were not so advanced. Even these mobile sensors, some, discovery of, say, 15, 20 years, And then our next generation will come and say that, look, our fathers were not having, these facilities, these discoveries, and then it will move on. So Plato says that there are many secrets hidden behind the curtain. You have to lift the curtain in order to know the truth. So therefore, in astronomy, in physics, many more things, sir, you will enlighten me, because many more things are likely to come to surface. Still, we have not been able to discover the secrets of our cosmos. So this is wonderful opportunity for our students to interact with great, scholars across the globe, and see what are chances in order to improve our knowledge, in order to improve our quality of education. So these are, these things are to be underlined. But one thing let me suggest, that I don't know whether Professor Kembhavi will agree with me or not. But by saying goodbye to our tradition and picking up other side of the globe, where everything is within physics and within, say, astronomy and cosmology, I mean, that should not happen. You have to combine it. I don't know. I will not talk about our Indian knowledge system, but I emphasize this fact that in the medieval time, a lot of interactions taken place between Central Asian scholars and Indians. You see, they sat together. They created a laboratory also on understanding, and then still our tradition, our traditional knowledge remained intact. So can we do it? All these advancements on one hand. On the other hand, can we develop ourselves as a combination of tradition and modernity both? Only modernity will not help. Otherwise, what you will do? What exactly you have been doing in the Gulf? So there is a room for humanity also. Let us create this kind of feeling amongst people, our students, that look, you can create anything. You can go. All sorts of knowledge available today. Physics, everything is, related to physics. You can make yourself rich by having all these formulas with you. But can you enrich the feeling of oneness? That is also important. We should not forget that when we are advancing our knowledge, we should also take humility together. One side business is not really very, very helpful to us. And what will happen is all these arms and ammunitions we have been producing, what has happened? They are all consumed in the Gulf. And, all countries are involved. They are suffering. People are suffering. The heads are not suffering. Then innocent girls, 170 innocent girls were bombarded very badly. They lost their lives. Look at their mothers, their parents, their friends, associates. What is happening there? Because we are not thinking, we are not sensitive about humanity. How much it costs. This workshop, you go ahead, you do all experiments, you pick up everything, you learn. There are great scholars here around you. But maintain this decorum that you are there to work for humanity. Not just your goal, set your goal, but your goal is not towards destruction. Rather, it should be towards construction. And I'm also of the opinion that this data collection, of course, through these professors, scholars, astronomical data. But last, not the least, I tell you, there's some words, I'm, a student of literature, and I don't know whether a poet also, but somehow, I feel like कि दरियाओं के मिलने से समंदर नहीं बनता. दरियाओं के मिलने से समंदर नहीं बनता. हाथों की लकीरों से मुकद्दर नहीं बनता. आईना बदलने से बदलती नहीं तस्वीर. आईना बदलने से बदलती नहीं तस्वीर. पानी कहीं जम जाए तो पत्थर नहीं बनता. Now with this hope that we will exercise our options every now and then, keeping in mind, but this is entirely in the interest of people, interest of our institutions, interest of humanity. Thank you very much.
Thank you, sir, for your encouraging and insightful address. As we conclude the inaugural session, I now invite our research scholar, Mr. Ayas, to deliver the vote of thanks.
Thank you so much, sir, for inviting me to present vote of thanks. Honorable Chief Guest, respected Chairperson, distinguished members of the Scientific Organizing Committee, faculty members, researchers, and dear participants. As we conclude this formal inaugural program for Virtual Observatory for Education 2026 workshop, it is my honor to express our heartfelt gratitude to everyone who has made this opening ceremony a success. We are deeply grateful to our eminent speakers and guests for their presence and for sharing such inspiring words, which have perfectly set the stage for the next 3 days of learning. We express sincere gratitude to our Honorable Vice Chancellor, Sir, Padma Shri Professor Syed Anur Hasan, Sir, and the Registrar, Professor S.K. Istiaq Ahmed, Sir. Due to some unforeseen circumstances, Sir, we are unable to join us. We are sorry for that. And the Dean, School of Sciences, Professor H. Alim Basa, Sir, and the Head of the Department, Professor Rafiq Abu Turab, Sir, for their constant encouragement and for providing the institutional support necessary to host such event of this magnitude. Our sincere thanks to Workshop Chair Shinzu Shu and Co-Chair Dr. Priya Hassan, as well as the entire Scientific Organizing Committee. Your vision in hosting the virtual observatory workshop at Maulana Azad National Urdu University is truly transformative for our research community. We extend our sincere thanks to IUCA, IVOA, which is International Virtual Observatory Alliance, and the BRICS Astronomy for their continued support in making this international collaboration possible. We highly commend the efforts of the local organizing committee, technical staffs, and those who have worked so efficiently behind the scene to facilitate a smooth start to this workshop. With the formal inaugural concluded, we now initiate our technical sessions and research discussion that are the heart of this workshop. We are privileged to have the keynote address on AI astronomy, AI basics and astronomy applications, and this will be followed by a session on teaching and education resources for virtual observatory, which will be conducted online. We look forward to welcome all the participants and wish you a productive series of sessions that we are confident will be both most fruitful and truly enriching. Thank you.
Thank you, Ayas. Now I request everyone to rise for the national anthem.
Jaya Jaya Mangala Dayaka Jaya He Jaya Jaya
Please be seated. We will now take a short break for tea, and after that, we will have an inaugural talk by our keynote speaker. Before ending, I would like to say one line. सितारों से आगे जहां और भी है. Let us continue the journey of knowledge and beyond boundaries after the break. Thank you one and all.
Hello, say 10:30 break. It's okay. The lecture will start at 10:30.
So next session will be going to start at around 10:30
It's
sharp.
already 10:30. In 15 minutes, 10:40.
Within short break of 15 minutes.
Might take briefly
of science. And those who the center and about 6,000 Kelvin at the surface. So because of the gradient, radiation moves upward. When it comes to the polar layers, then the radiation gets absorbed. The absorption depends upon the thermodynamic state of gas and chemical composition. So the study of the spectrum really depends on what the chemical, what the spectrum of the star. Now, what is the chemical composition of the star? And so now here, now this is a picture which is for the space telescope. And you can see here mostly. I showed you in the beginning of the data part a picture of the sky, and where every object was a star. But here, this is a very small section of the sky observed with the Hubble Space Telescope. And unlike in the previous one, every object, almost every object here, is actually a galaxy. So, for example, this object is a star because you can see the diffraction pattern. It's a point source. But these things are all galaxies. And you see that this small little dot here, that's also a galaxy. Right? And then how do we know that it's a galaxy? I'll come to that later. That's an application we have. And then, so you see that this, our galaxy has got 10 raised to 11 stars. And this tiny object here could have 10 raised to 11 stars. Right? So 10 raised to 11 stars. Now we know that every star has got a number of planets on it. So you're talking about 10 raised to 11 or 10 raised to 12 planets. So even if there's a small probability that the planet will have advanced civilization. Okay, that means that in that one dot, you are talking about between, say, 10,000 and 10 million civilizations. And then if you do look at count the number of galaxies that you see in the sky, it's about 10 raised to 11. So that tells you how much thing is there. And now, of course, each galaxy, you can zoom in on it, more or less depending upon how far it is, and study it. Right, and so now this is a spectrum of a galaxy. So what does the galaxy consist of? So our galaxy consists of stars, and then it has got gas, it has got dust. And there are stars which are being formed and stars which are bursting out into planetary nebulae, supernovae. So then when the galaxy, so you can get the spectrum of the galaxies, which is the sum total of the spectrum of all the stars and the gas and the dust. The dust may emit itself if it is hot, but otherwise it affects the spectrum which is emitted by the others. So you can see here that the spectrum of the star is very clean, in the sense that it is like a black body. Here you have got lots of stars at different temperatures, different luminosities, and the typical galaxy spectrum looks like this. Okay, but this is a completely different kind of object. It is what is called a quasar. So at the centers of certain galaxies, you have got what is known as active galactic nucleus. So the standard picture of an AGN, which may or may not be correct, is that it's a supermassive black hole, which is accreting matter from its depth. And as the matter falls, it becomes very hot. It starts emitting radiation. And it emits emission lines. So in stars, you have got absorption lines. So galaxies, you have got absorption lines. But from the center of the galaxy, you get these emission lines. And once you've got the emission line, of course, then you can do the same kind of physics that you can do, physical investigations that you can do as with stars, except that here, the nature of the physics is quite different. Now, this is the modern way of doing things. So you see, I talked about the spectrum of a galaxy, but you can ask me a spectrum from where? Because the galaxy is an extended object. The central parts of the galaxy can be quite different from the peripheral parts. So what you would like ideally is not just one added spectrum of the galaxy, but the spectrum from each pixel. That's a tall order, because how do you get a spectrum from each pixel? You take a fiber and put it behind each pixel, right? And then you take the fiber to a spectrograph. So you can imagine how large it will be. I mean, it can be as half the size of this book. It's called an IF integrated circuit. Okay, then so you see that you have got a spectrum coming from each part of the galaxy. So then what is the data become? And in the parlance of AI, The data is now a tensor. What do you mean by that? You see that a spectrum is a one-dimensional object because at every wavelength I've got an intensity. I do plot it. An image of a galaxy is two-dimensional, right? Because I'm seeing it there. But now I'm getting a spectrum from each. So what I can do is that how will I get a spectrum? I will get it at one wavelength and the other wavelength and the other wavelength. So two dimensions combined with the third dimension. So then what you have? You see that this is the picture of the galaxy at this wavelength, 7,000 angstroms. If you have a picture here, you get it at 4,000 angstroms. So what happens is that you're taking a two-dimensional image and stacking it. So your data becomes three-dimensional. And in data analysis, it's called a tensors. I mean, if you're doing general relativity, the tensor will be a far more complicated object. But here is more of stacking the data together. And here is the transient, a picture of the galaxy taken at one time, the same galaxy another time in the new object. And that's a superfluid. Right, and you can see, what is this? Sorry, I forgot another transient there. And this is a completely different kind of data. So here you've got a galaxy which is Centaurus A. The galaxy is somewhere here, and the optical galaxy, and these are radio lobes which are coming out. And these radio lobes, in order to get the radio data, you need to use a radio telescope, like the GMRT which you have in Apple, which is perfect for producing images like this. And these are the contours of the radio emission. And then on top of that, the red colors that you see are the X-ray emission. So you see that this is what is known as multi-wavelength astronomy. Start with optical objects, superpose on that the radio data, and superpose on that the X-ray data. So you say, how am I going to do this? I mean, it's going to take me years to do this. But I don't know if I'm going to introduce you to it now. But there's a place called Astronomical Data Center in Strasbourg, in France, and which is probably the most important astronomical data center. And there they develop a number of tools. And this has taken place over the last 35 years. When we first started IUCA, I did data for them, and I wrote to them, and then over a period of time, they sent me a big box full of large tapes. So I get a student to spend 6 months reading these tapes. Now it's all online, and you've got different tools. For example, you've got a tool called Kembhavi. So there you can just put in the name of an object and you'll get all the information about it. Then you've got to do a Vizier. They have all the names from the Arabian Nights. Okay, so you've got Vizier. What Vizier does is that it just gives you all the catalogs you can imagine. You can go to any catalog published anywhere and look at it. And then there is an amazing thing called Aladdin. And like you rub the Aladdin lamp and you can get genie out of it. So Aladdin is just perfect to very quickly. And if you are using Aladdin and you try to do that here, you just say send A and give me the optical data, the radio X-ray data, and you do this image immediately. And so it's all quite easy to do. There it is. So, so the data is in abundance, and then what you want to do is now to find ways of analyzing data, getting the astrophysics. Right, so this is a pulsar, radio pulsar. Yeah, and what's the time? So this is the gravitational wave detection, the first ever gravitational wave detection, and 150916. Meaning they were detected 2016 September. And so what was detected? So there are two black holes which are going around each other, and they are very close by. And so they are going on very rapidly. And such a system emits gravitational waves. As it loses energy, the total energy becomes more negative. So which means that the system will shrink. And it comes closer and closer, and then the two black holes merge into each other, and then they become a single black hole. Right, and this will be a curved black hole, meaning that it will have mass and it will have rotation. And these are not artificial impression. I mean, these are all numerical simulations. And you can see here is the actual fitted data. And you can see that these are the oscillations, these are the things that are going around. And in the case of gravitational waves, the frequency of the radiation which is emitted is twice the frequency of rotation. And you see that you are seeing only several rotations, and here you are merging into star. And after the merging is done, you have got what is known as ring down. Okay, so what is a ring down? Then you go and hit a bell in the temple, and then you leave it, and then you see that it gradually the frequency is skipping. It's a very beautiful ring. And so this is ringing. It was first talked about by Professor C.V. Visher, okay, in 1970. And then, and then how much time has all this taken? It has taken 0.7 seconds, no, 0.1 second actually. You see here it is 0.3, here it is 0.4, 0.5 or 0.2 seconds. And what has happened in 0.2 seconds? There are two black holes. One has got a mass of 40 solar masses or so, the other one is a little bit less than that. And then they are merged together, and a single black hole has been formed. And then there's a difference in mass of several solar masses, and that has gone as gravitational energy. And the fun is that this is absolutely invisible in the electromagnetic. So either gravitational waves or nothing. So now, quickly, so now when there are different ways of getting data. One way is to get the data from individual objects and collect it together. The other way is to observe the sky. So you can have a telescope, for example, the Sloan telescope, which is about 2.2 meters, I think, 2 meters. And so that telescope just keeps scanning the sky every day in 5 filters. And then the data, this is 2021 data, it keeps increasing. So you see that it has got 260 million stars and 4.8 million spectra and so forth, and 126 terabyte. So you see that there is an extreme abundance. And what they do is that they have got these pipelines which give you the primary properties of the objects. It can tell you, for example, that the object is a galaxy or stuff. And so these things. Now you can easily download the data. Maybe it is a part of your hands-on sessions here. You can easily download the data and analyze it. Right. So now this is the more modern thing. There's an observatory called Gaia, which observes stars in our galaxy. And look at the numbers here. So you've got accurate stellar position for 1.8 billion stars. Right, and then 1.4 of parallaxes and proper motions. What do you mean by parallax and proper motion? Is that if there's a star about say 5 light years away, the closest star, I can observe the star today. And when the Earth is at some point in orbit, I can observe 6 months later. When it is at the diametrically opposite point. And so I got a triangle like this. I know the base, which is 150 million. No, it's 300 million kilometers. Okay, and because the distance to the sun is 150 million kilometers. And I know the angle. Right, so I can solve the triangle and get the distance to the star. But as the star goes further and further, the angle becomes smaller and smaller. Right, so therefore, beyond about 50 light years, this doesn't work. But Gaia is in orbit, a very large orbit, and therefore it has got a very large baseline. It is not limited to the baseline of the area. And then it observes, and then it gets positions to lots of these stars, and it gets proper motions. So you have got a parallax, and proper motion is a motion in the sky. Because the spectrum it knows how to go in, you can see the lateral motion. So which means that you've got a 3-dimensional information about the star. And then you have got a map of the galaxies. So then the data release 3 of Gaia, which happened on 13th June 2022, you see that you've got 1.8 billion stars with all these. So there is an amazing amount of work that we can do with this kind of data. So if you decide to observe yourself, what are the kind of observing facilities that you have here? This is a GMR, and it is one of the world's largest radio telescopes. Then this is the Gamma Ray telescope in Hagley. And you've got the 3.6 meter Devasthar optical telescope, which belongs to Aries Observatory, because these are all national facilities. The PRL 2.5 meters, and this is the Hagley telescope, which is also the same place as that. And these are 2.5 meters. And they have been performing extremely well. And then we have got these three wonderful observatories. One of them is AstroSat, which was launched in 2016 with the expectation that it will be there for 5 years. But it's been recently 10 years of the data taking for celebrating. And then here you have ExpoSat, which is for X-ray polarization. And then there is a very interesting Aditya mission, where you have got this the satellite at what is known as the first Lagrangian point. The first Lagrangian point was between the Earth and the Sun, and you put it there because if the satellite stays there in a small one, and then you point it to the Sun, and it remains forever pointed to the Sun. So which means that you're observing the Sun continuously. The James Webb Space Telescope is the exact opposite of that. It is at the second Lagrangian point, which is you take the Sun, join it to the Earth, and produce it outside 1.5 million kilometers. There is the second Lagrangian point. JWST is there, and it keeps looking away from the Sun. So which means that you can observe the dark sky continuously, and you're getting marvelous data from that. And there are future facilities. The LIGO India gravitational wave detector, which is already being, it is going to start construction by soon. This is the 30-meter telescope, which is in big trouble. India is a partner in that. And then about a square kilometer array, and it is a giant radio telescope. Half of it is in South Africa and half of it is Australia. And India is again an important partner for this particular telescope. And so recently, in the last budget, the union budget, the finance minister okayed some other optical facilities. So one of which is what's called a national large optical telescope, and that will be 13.7 meters. Right, and then there is a solar telescope, which also has been approved, and the upgradation of the telescope, the XCTS. So you say why 13.7 meters? Why not 13.6? Why not 13.8? Why not 14? That comes out of the constraints in the construction of the telescope, because it is not a single mirror that you have your segmented to anyway. And so now I want to show you something here. When you study the sun, for example, we study it as a star. But look at what is happening here. You've got the Earth, and then the charged particles which are rushing towards the Earth. And so they can set up a magnetic storm. And this is real, it's not a simulation. So, you can see there's a magnetic storm which takes place. And you see that we are dependent for every second of our life on satellites in space. So, for example, if you now leave this place and you want to go back to wherever you come from, or to the hostel where you stay, you will use Google Maps. Right? And so all of that can get completely disturbed because of the solar wind lines. So you want to study the sun, not only for the astrophysical insights that you get into it, but because of this very primary consideration. And this is of strategic importance, because it is the wars which are going on now. I mean, they're all very heavily dependent on electronics. They're heavily dependent on missiles which are being guided. And all of that completely go nuts the solar wind lines. Right? So then of course, on the beauty side, you get these northern lights, which is the effect of the solar winds. So Priya, should I stop there? Yes, I think changing was the exact 40 minutes.
Yeah, we can take a couple of questions.
Yes.
Any questions? Please, you're offline. Please make the
You said that 0.2 seconds for the black and further to take place, but
Yeah.
while the black is not coming together, like closer each other,
Yes.
then certain change in the frequency. Didn't you observe that?
Yes, you are observing. See that whatever you are seeing there is real. It is not a model. It's real data. So you are seeing the change in the frequency. And typically what happens is that the LIGO thing, you see that the frequency, what you do that if you have a time dependent signal like that, time dependent signal, you take a Fourier transform and it will give you all the frequencies. So LIGO is mainly sensitive between 20 Hz and 40 Hz. Okay, and it is about 100 Hz. So you are measuring, you are doing the frequency in that narrow band.
So my question is that by seeing that change in frequency, we can predict like what is the time and where it's going to work, and then we can confidently.
You see that the problem is that when it is far away, you saw the 0.2 seconds, and before that the gravitational waves emitted a little bit, so you can't predict. Otherwise, you'll be able to predict that say this is not one. You can't do that, and it is possible in the future. There's something called decihertz gravitational wave. Okay, with frequency like 0.1 to 1 hertz. And then you can see, for example, these things which are quite far. Then you can say that already you're going to get a merger at this. It's all very early days. We have detected about 200 sources in 10 years in 4 observing lines. And then we'll get more and more things.
Yeah, you said about cut, it is cut black.
Yeah.
So how do you know it is cut black? Because it is a model.
You don't consider charge because all astrophysical black holes are new. So because they are formed from astrophysical matter. That doesn't matter because how do the black holes are formed? They are typically through the evolution of stars. Right? And then evolution of stars. And then you see what happens there is because the evolution, because they come from stars, they are neutral. Now, I said that you think it's a current black hole. Because there's a mass, there's a spin you can do. But the whole thing is dependent on something which is called, we've got a model which assumes that it is a merging black hole. Now, in some cases, the data is so wonderful that you have no doubt that there is. In other cases, the data is a bit dicey. At which point you don't know. And it can be other types of source. In fact, I was writing about this, that I can give that to you. I write these black hole stories. And so currently I'm writing on the life of black hole. If you see me afterwards, I'll show you. Yeah.
How do we know that gravitational waves is gravitational waves? It may be some distortions. There are so much distortions.
You know in the gravitational wave because you're taking into the gravitational wave. Yes. Okay, so what a gravitational wave does is that as it is passing through, it changes the structure of space. Right? So then if you've got a bar, the bar will start oscillating. Right? So you've got the detector there, and so you detect the signal gravitation. So I can say it may not be coming from a merging binary, but we know for sure it's gravitational waves.
It may be tectonic plates.
That's all removed. That's all. You see the thing is that forget tectonic plates. Tectonic plates take a long time. If you walk, there's a gravitational wave detector. If you walk, it causes a disturbance. If there's a sea which is 150 kilometers, it will cause a disturbance. So all the gravitational wave detectors and the people who do that spend all their energy removing noise. So why did it take so 20 years to detect that? Because you have to learn how to remove the noise. The gravitational wave signal is extremely tiny. Yeah.
This LIGO India project that is going to come to India, like how would it compare to already present LIGO that is?
It's the same.
Like it's ready like better than?
No, you see, what will happen? The LIGO started with a detector called initial LIGO. That did not do anything. Then it went to advanced LIGO. And advanced LIGO was there until 2000. But this was just before the start of it. Okay, then concept totally died off. So they have got to A plus. The detector for A plus. So when you go from one detector to our next generation, you are improving the sensitivity, like the signals are not signals. Then so that is where we have the present time. So when India builds a detector, it will be using the latest technology that will do that. So what is the beauty is the distance from the other two. And that gives you a long pathway which allows localized. That is the most important category.
So let's thank Ajit. We're going to hear him again. There's going to be a.
I'm here until 5 o'clock.
Yeah.
Perhaps you can please see me during lunchtime and the last question.
And we have another talk by Ajit also, but in between that, we have one by Cheng Zui, which we'll start. Sorry.
Oh, yeah, no, I'm very happy. That's fine.
Yeah. So Cheng Zui, I will. Yeah.
Chen Zhu
Yeah.
is a very senior Chinese VO person. I know him very well. I've known him for decades. And even though he's very senior, you see that he always looks like a boy. So he has that good fortune.
Yeah. Cheng Zui, I would request you to start. You can start sharing your screen.
Yeah, hello everyone. Can you hear me?
Yeah. 1 minute. 1 minute.
I share my screen.
Yeah, you can. 1 minute.
Okay.
Yeah, this guy is.
Yeah. Okay. Good.
No, mine. I'm trying to
Hello,
look for
everyone.
my own thing. Yeah. This is my.
I'm Chen Zhui, from National Astronomical Observatory of China. I'm sorry that I can't join you in person this time. So I'm very happy to give the talk about virtual observatory resources for teaching and education. This is content.
1 minute. 1 minute. Cheng Zui, 1 minute. I just need to adjust the audio.
Yeah, I would like to give a basic introduction about virtual observatory and the International Virtual Observatory Alliance. And then there will be a comprehensive introduction about VO resources.
Just a minute. Just wait. Just 2 minutes.
Sorry, Priya. Any problem? Could I go ahead? Hello? Priya, can you hear me? Can you hear me? Hello? Is everything okay?
Yeah, we can. Yeah, you start.
Okay, so I go ahead. The third part of my talk is about astroinformatics resources. At the end, there will be a very brief summary of my talk. Just as we learned from the talk of Ajit Kembhavi, astronomy nowadays become a data-driven science. Since the beginning of this century, leading by, for example, 2DF SDSS, and some other world-leading sky survey products. The astronomy stepped into terabytes area. And about 15 years ago, leading by, for example, Gaia FAST means 500-meter radio telescope in China, and recently the LSST and Euclid, the astronomy, the data volume in astronomy stepped into petabytes to exabytes today. Now, astronomy is entering an era of big data where the data size are too large to download and analyze using users' own facility is not possible. So our traditional research programs, that means you browse data from the web browser and download to your laptop or personal desktop, then analyze and computing is more and more infeasible. So currently, cloud computing and AI becomes the new solution. At the beginning of this central, the leading astronomers and IT experts realized the challenges to astronomers and to the astronomical community. They initiated the idea of a virtual observatory. Here is a vision of the VO. The web is transparent, and the goal of the virtual observatory is to achieve the same feeling for astronomical data. That means all available to explore in a single transparent system. Astronomical data sets, tools, and services should work seamlessly together. The VO allows astronomers to interrogate multiple data centers in a seamless and transparent way, provides new powerful analysis and visualization tools within that system, and gives data centers a standard framework for publishing and delivering services using their data. A summary for the virtual observatory, like the worldwide telescope, the VO is not a flexed system, but rather a way of doing things. Now we are facing new challenges in AI area. The sentence in blue is my definition for virtual observatory. VO is a data-intensively online astronomical research and education environment, taking advantages of advanced information technologies to achieve seamless global access to astronomical information. The global community to push the VO initiative forward. We established the International Virtual Observatory Alliance. The Alliance is an organization that debates and agrees the technical standards that are needed to make the VO possible, a focal point for VO aspirations, and a framework for discussing and sharing VO ideas and technologies. The IVOA was created in 2002. Currently, there are 23 national and international projects members. There are 6 working groups and 9 interest groups. For the IVOA, we organize 2 interoperability meetings per year. Usually, the spring meeting is in May, and the fall meeting is in November. This year, the spring meeting will be held in CDS in June, and the fall meeting will be held in Perth, Australia in November. During the last more than 20 years, there are about 50 interoperability standards and specifications have been defined by the airlines. Here you can see the group photo for 23 VO project members and the architecture for IVOA working group and interest groups. Next, I hope to give you a whole schema for what is a virtual observatory. As we know, if we do astronomical research, we need some resources, including astronomical data, computing facilities, storage, software, a telescope, and other instruments and facilities. This compromise the research resource for astronomers or for you. And here is a resource layer. And for users means human users, individuals, and our computer users, Python programs, and AI agents. And so the IVOA, or the virtual observatory, is to hope to using advanced technologies to share the resources, research resources to its users. The how to realize the goals. So we need sharing these resources. For users, first, you have to find what resources are available for you, and then you should have the ability to get or to access, to use these resources. Then this is a very brief working flow of virtual observatory. That means virtual observatory core realize or enable the resources are shared to the users in a transparent, seamless way. Yeah, it's easy to say, but not easy to realize. To realize the ideal goals of the virtual observatory, we have defined a set of interoperability standards. These standards will provide data and metadata collections, provide a registry to let users find the resources available to users, and provide data access protocols to individual users and Python or programming users. For the VO, how to realize the whole system? We must define formats, data formats for our catalogs, image set, data cubes, spectrums. And we need to define semantics for our astronomical data and services. And then we also need define the data models for different observations and different data sets. We also need a standard query languages. I guess most of the participants of our workshop has some understanding about SQL, means standard query language to access database. But a standard SQL language is not enough for astronomical queries. For example, the RA or declination DEC and astronomical coordinations are not easy to realize in traditional database systems. So we need to define an astronomical-oriented query languages. At the application level, we also need some specifications. For example, how to realize message exchange among different applications, and how to standardize the messaging or communication methods. And we also need standardize the user interfaces. So here is a level 2 of the IVOA architecture. From the level 0 and the level 1, you have realized the whole working principle for the virtual observatory. So here you can see many specific IVOA standards defined during the last decades. Here is very detailed for the virtual observatory architecture. If you are interested, I encourage you to browse the IVOA website and learn in detail about each specifications. In data science area, they have a principle, means FAIR. FAIR means flexible, interoperable, accessible, and reusable. Just learned from the IVOA architecture, we know the IVOA, the VO architecture is a fiable data architecture for astronomy, for astronomers. Yeah, so we are very happy. Fiable or FAIR principle was initiated about 2016. However, the VO idea was initiated in about 2000 years. So astronomers are very smart. Okay, so since this time, I will share you the teaching and education resources from the whole VO community and astroinformatics community to you. Each resource, I will provide you the URL, and you can follow the links to get more information. The first or the entrance for VO resources should be the IVOA website and the wiki pages. Just several days ago, the IVOA released a new version for its users. The new design is more user-friendly, and you can have a look from the screen capture on the left. From the IVOA website, there are many informations, and almost all documents, meeting notes, and slides from working groups and interest groups were collected here for the last 25 years. And from the IVOA meeting, there is a calendar here. This is the calendar. And you can see the coming meetings in this year. And you can find links for the past meetings. Here you can learn the detailed information for each working groups and interest groups. Also, we have provided the page for each IVOA defined documents and the notes here. So, IVOA website and Wikipedias are very important for you to get information and resources. For education and teaching, IVOA established an interest group, education interest group. Here is a wiki page for the interest group. From this page, we collected information and resources, tutorials on education and teaching. Of course, most of the information of my slides, my talk, have been collected here. This page was established by myself several years ago. Of course, your contributions are very welcome. If you have new resources or new links about education and teaching, welcome send to me or send to Priya and some other speakers here. For newcomers of the Virtual Observatory, at the IVOA website, we provided information for newcomers. Here is a starting point and the materials to start grabbing the basics of the IVOA and the VO world. Currently, there are two parts. The part one will introduce to some of the VO standards following a multi-messenger use case from the user's perspective. And the part two of the tutorial will show selected steps of the first part tutorial from the perspective of the data provider. The question here is, what does it need from the perspective of a data provider to enable the user experience of part one? So the IVOA website, we have several kinds of audience. For example, scientists or astronomers, developers, and members. So if you have different requirements, you can follow different channels of the website. The next very important or classic resource on virtual observatory is a book. The book, the name is the NVO, National Astronomical Observatory, Tools and Technologies for Astronomical Research. This book was compared by US VO project and published by ASP in 2007. There are 6 9 captures. You can see there are 7 sections from introduction to VO tools, science with VO, technologies and protocols, discovering and registering resources, accessing data, publishing data, foundation technologies. The book was based on the US VO summer meetings in 2004, 2005, and 2006. So these materials are still available from the following link. You can get the whole textbook. And the Chinese Virtual Observatory project translated this book into Chinese and published the book in 2010. Next is from EuroVO. EuroVO means Virtual Observatory of Europe. The EuroVO put a lot of efforts on education and tutorials. So unfortunately, the EuroVO project has been frozen for several years. However, their resources and web pages are still accessible. Here you can see their website. They provided scientific tutorials and education pages. Here you can see some use cases, tutorials, and then interactive Jupyter book tutorials. You can follow using a Jupyter notebook environment step by step. Here is an example from EuroVO for education. EuroVO for education is a project developed within the framework of the whole EuroVO with the aim of diffusing EuroVO data and software to the public, in particularly students, teachers, and astronomy enthusiasts. And the usage examples are in the form of Panigonic modulus consisting of 2 main parts. The first part presents a typical astronomical problems with a short introduction and a description of the solution found by astronomers. And the second part is a step-by-step guide to the commands needed to reach the solution of the program using Aladdin or Stellarium. So these usage examples aim at familiarizing the user with Aladdin and Stellarium and at simulating further interest and activities in astronomy. There are more than a dozen of use cases you can follow. For example, there from the screen capture, we listed several examples. The sky, the stars, the shape of galaxies, the placid open cluster. So you are encouraged to follow the step-by-step tutorials from the EuroVO for education. This is a detailed example from the project from ESA. The Darren has been working with translation and updating some tutorials for VO education, and he uses cases for updating the tutorial, calculating the redshift of galaxies. And the goal of this tutorial is to compare the spectra of different galaxies and calculate their redshift, and hence search for evidence of the expansion of the universe. You need to learn to use CASIS and NIST Atomic Spectral Database Service, the NASA IPAC NET database, and TopCat tool. The next one is about CDS. CDS is a very powerful and reachable web portal and services. I guess many of you have been used or learned about services from CDS. For example, Simbad, Wizra, Aladdin, or some other tools from the CDS. The CDS provided updated tutorials and examples how to use CDS services. You can see from the content of the CDS tutorials, they give you introduction to using the CDS services with Python, first steps with MOC data structure, the simple spectral access protocol, and combining the CDS services to study gamma ray and high energy spectral bands. Yeah, of course, from the link, from the bottom link, you can get all the contents of the tutorials from CDS. Another resource is from the Spanish VO. Spanish VO, they organize the education workshop each year, and they collected their slides and tutorials on their websites. Usually, the contents from Spanish VO is in Spanish. Several of them, or part of them, are in English. So if you are, of course, you can learn these materials with the help of large language models or translated online by your web browser. And these slides show the information from GAO. GAO means German Astronomy Astrophysical Virtual Observatory. They provided several tutorials on astronomical data query language, ADQL, and ADQL hands-on course, and their tutorials main coverage astrometric, Club Aladdin, registry, data discovery, TopCat, Python VO, simulations, and TAP protocols. That means GAO provided several selected tools and specifications to their users. Here is an example for the VOTT. VOTT means Virtual Observatory Text Treasures. Is a formatted list of educational and outreach tactics on using the VO, including use cases, tutorials, courses, and such. VOTT contains materials for all settings, from preschool to graduate, and it is generated from the documents known to the VO registry. So here they provided different levels, materials for schools and outreach use, more advanced material suitable for advanced high school students or amateur astronomers, and material targeted at university students and researchers waiting to learn about the VO. So from this website, you can get suitable level contents for you. And they also provided tutorials in several languages, including English, Italian, German, French, Spanish, and even Japanese. This page shows about information from Armenian Virtual Observatory. Armenian Virtual Observatory is an active member will project among the IVOA. They organized during the last 2 decades, Armenian VO organized very successful summer schools. For example, last year, they organized the Brakan International Summer School and the Brakan Astronomical Meeting on Astronomical Service and Big Data. From the website link, you can download the slides from speakers. They are very useful for you to get information for the virtual observatory and big data and machine learning. Last year, both Ajit Kembhavi and me attended the Armenia Virtual Observatory summer school and meetings. This is meetings for last year. And here I also provided you the links to the meeting. Next one is from Japanese Virtual Observatory. They provided some workshops for education for teachers and students during the last some years. Unfortunately, their workshops were stopped since 2006. However, if you are interested in Japanese on the NAOJ, you are welcome to visit the website and get more information. The NAOC or Japanese VO, they keep very close collaboration with ARMA project, and they provided ARMA data access, and related tools to analyze ARMA data. Next part of my talk is about resources for astroinformatics. Astroinformatics is a wider paradigm combine information technology and astronomical research. Here, the first portal for astroinformatics is the International Astroinformatics Association. This is a website. You can see the link of the website. They provided useful links and resources, general data science and astroinformatics, software resources and links, learning resources, astroinformatics literature, and funding opportunities. Hope the funding opportunities are still available for you. And from the online courses, you can get some information, more detailed information provided by Penn State University. Here is the logo, and the Penn State University, ASAIP, the Austro Statistics and the Austro Informatics Portal, is a new website serving the cross-disciplinary scientists, and it is intended to foster research into advanced methodologies for astronomical research. So here is an example for software tutorial and online courses for data-driven astronomy and some other informations. You can explore from the website. This one is a course from Caltech, Astroinformatics. This is a very popular course in Caltech. The speaker or instructor of this course is George Jovsky, and Ashish Mahabal. He's an Indian astronomer, and some other instructors. From the link, you can get information from this course. They are very valuable for you. Another one is from Northern Arizona University. This course is also named Astroinformatics, Big Data in Astronomy. However, from this link, the information is limited, but you can get some basic information of this for this course. Another one is Astronomy 630 on Statistics. This course is from New Mexico State University, and they provided lecture notes in PDF and the Python toolkits. Several 10 years ago, the University of Belgrade, they designed a whole 4-year-long astroinformatics courses. However, this course set continued only very few years. From the first year to the second year, third year, and fourth year, they list a whole courses for astroinformatics students. This link is broken now, but you can get from my historical screen capture how they organize the different courses together for a whole university-long study. This one is an updated course from University of Belgrade. They provided the S3 astroinformatics, astrostatistics, and machine learning in astronomy. So here is learning outcomes, knowledge, understanding, and applying knowledge and understanding for the course. Here is the link for this course. For the Italian VO, they also organized several very useful workshops on data mining and exploration. Here is a course for astroinformatics collected by the University of Federico II of Naples. This workshop was organized Caltech, IBOA, EuroVO together. You can see the lectures structure from ESS to work to data warehouse, virtual observatory, database management, database information, Python, machine learning, supervised machine learning, and the fuzzy logic, TDA, time domain astronomy, unsupervised machine learning, fundamental of C, C++, and deep learning, and many others. So it is very useful for you to get some basic skills and information for machine learning and deep learnings. This one is from University of Chile. They provided the Austrian mathematics course for Faculty of Physical and Mathematical Science. Provided statistics for astronomy, astronomical data, machine learning, temporal and spectral analysis, HPC, high performance computing, and a student group project. This is the link of their course and courses in notebooks. Another one, this is from ISA, from Spanish VO, from AC, Institute of also Carinata from Spanish. They organized 2 workshops and provided lectures online. So the workshop, the winter school of astrophysics focused on big data analysis in astronomy. So there are the famous speakers, George Jofsky from Caltech. They attended the workshop and provided lectures. This one is from Chinese Virtual Observatory. Since 2001, the China VO will organize a national virtual meeting in China, in different cities in China. So we collected all the slides here. So if you are interested for the VO activities in China, you are welcome to visit the link. And you can get a very clear history development of Chinese virtual observatory and what is continuing, what is going on in China in the astronomical information. And for education and public outreach, we provided a specific channel. Here, you can get for resources about Worldwide Telescope, Citizen Science Project, the IAU Date-Driven Astronomical Education and Public Outreach Working Group, ESA Sky Chinese version, and many other education services and resources. Since 2024, we provided astroinformatics course to the students at Chinese Academy of Sciences. Here is our structure of the course, from introduction to VO and astroinformatics, mathematics, to fundamental technologies, fundamental of astronomical data, VO tools, services, visualization, visual analytics, and big data, data science, and AI and machine learning. So we have completed 3 times teaching in the University of Chinese Academy of Sciences. Additionally, we also published a textbook. Here you can see the textbook in Chinese. Yeah. Additionally, in Taiwan, the Taiwan province, they also opened the course on astroinformatics for academic year 2023. This is an astronomer, Japanese astronomer, working at the Graduate Institute of Astronomy, NCU in Taiwan. Here I provided the link to this class. So the last, but not the least, is a class from Professor Alex Zali. Alex Zali is one of the initiator of virtual observatory, and he is also the SDSS Sloan Digital Sky Survey database designer. Alex Zali opened the course in Johns Hopkins University under the name of Beautiful Data: Introduction to Practical Data Science. Here you can see Professor Zali provided his presentations and videos. So this is also a very valuable teaching resource for you to learn data science and virtual observatory. This is my last slide. Lessons learned and conclusion. Since experience of last 2 decades, I learned tutorials and courses are very useful. On the other hand, preparing tutorials and courses are very time consuming. So let's enjoy these resources and appreciate the contributors. Keep materials up to date is a big challenge, since the technologies and the research paradigm are changing very fast. So how to keep materials up to date? It is a very time-consuming effort. Fortunately, large language models provided a great help for us. But AI is very powerful and helpful, but it must be used very careful. I'm sure all of us have been contacted or used large language models for research, for astronomical research. You must have your own skills and understanding of what is true and what is false, and know how to contact with AI. Seen from the following lectures of this VO for Education workshop, you will learn detailed information about large language models and machine learning, and you are welcome to feedback to us. Okay, thank you. This is my talk.
Thank you so much, Susan. Thanks so much. I'm sorry there's
Any questions or comments? Oh yeah, there are several hands-on. Then Oshika, can you speak? Maybe unmuted? Need unmuted. Priya, I can't hear you.
now you can. Yeah, but it is a.
Oshika has question.
Question is about the slides. I'll share them later. Yeah.
Okay.
So thanks a lot, Chengzu. Sorry for this problem, but thank you so much. Are there any questions here? Would anybody like to ask any questions? I can just check online. Yeah, so if you want to ask a question, please tell me. I will unmute you. The problem is that too many participants online, hence they are. So if people, one who's online wants to ask a question, please let me know. I'll unmute you. Okay, Anushka, take it. Okay, 1 minute. I'll just. Yeah. So you can unmute yourself and ask. Yeah.
Yeah, hello. Am I audible?
Yes.
Yeah, I just wanted to ask about the slides, but as you mentioned that you would be sharing them.
Yeah, we'll share them.
Yeah, that was all. Yeah. Thank you, Professor Koi, for such wonderful session and for sharing such useful resources. Thank you so much. It was a wonderful session.
You're welcome.
Yeah. So thanks a lot. Oops. Thanks a lot.
Okay.
So bye-bye. Thank you so much. Bye-bye.
Hello. Hello. Can you hear me there? Now? Is it okay?
Yeah.
You can hear me, right? Okay.
Oh, yeah, I can hear you.
Don't put the mic. You need this. No.
No. We'll.
Unmute that. Unmute that.
Yeah, mute it completely.
Yeah, I can hear you now.
Sorry, we are testing out things here.
Yeah, take your time.
Yeah.
There was a bit, but it's kind of sorted.
Now I think it's sorted. Whatever you speak through this, it will go.
Okay.
So now we don't have to put any microphone on them.
What do you mean?
No, you should just mute.
Okay.
Yeah. Are you on Zoom? You are going
Yeah.
on Zoom, right?
He will join.
I have to go on Zoom, right?
Yes. So you're unmuted, right?
Yes, please remain muted.
Unmute.
And we will check whether you can hear.
Yep.
Yeah. So Zoom.
That same link.
Yeah.
I'll have to make you co-host.
That I will do.
Recording in progress.
Do this as it is. Okay, and then share this. Whichever. For the full screen, whichever you.
Yeah. So Ajit, your co-host.
Yes.
Yes.
And now. Yes. This one, yeah.
Yeah, great.
Perfect. And can I use a color mic? Yes.
Yeah,
Come back in a moment.
Yeah, sure.
Let's test. Hello. Yeah.
Okay. Yeah, there's a little.
Hello.
1 minute, let me check.
Can you hear? Hello.
Yeah.
Okay, so come here. I will tell you what to do. See.
We played around it with a lot, yeah.
Yeah.
Then we
So
got
see,
confused.
there is a microphone here, right?
This is what we should use for this whole sound system.
This is whole that you should use, and make sure that this speaker is off
Okay.
while we are talking.
Okay.
So whatever they will ask, we won't be able to hear. Then if we want to hear what they are speaking, then we have to
Yes.
mute and then switch
Okay.
this. Otherwise, there is an echo and feedback.
Okay.
This is, unless you have noise cancelling microphone.
I
it
don't
won't
think
work.
that's
Yeah.
there. No, this is the
Yeah,
one
yeah.
that's the.
This is what's there. Okay. Yeah, okay.
Yeah, so we'll obviously share this slide later on. I'm still in the process of correcting him. After somebody was asking.
So I mean, until Ajit comes, I
Yeah.
just wanted to
Please
check.
come and introduce
How
yourself.
many, yeah, I'm Suraj Bore. I will also be
Yeah.
giving one lecture and then a hands-on session. So one of the questions that I wanted to ask is, how many of you are familiar with basic cosmology? Some of you, not all. Okay. Okay, so what I will do is I will try to introduce also some basic cosmology so that all of us are on the same page. Because I think there may be few people who may not be fully familiar. You heard about Kembhavi distances, luminosity distances. Okay, so we'll try to go through because that's the part that we'll need in the hands-on session. And I don't want anyone to be left behind. So we'll slowly go over it. Since there's one and a half hour. Okay. And Python notebooks, Python is okay. Is everyone without knowledge of Python? One. Any more? One. C++ is okay. C++ is okay. For the last day. Which one? No language. Okay, so it will be harder to follow. So I would suggest you to go to Python. But you said C++ is okay. No Python. Which one is okay? Yeah, which language is okay? C++ is okay. Okay, so I will send you code which works in C++ and then you can use that at some point. Not today, so you will have to work together with it. Okay, so you can put on this collar mic. Yes. And hopefully this time everyone will be able to hear you. Yes. Properly. Become wiser. It's not on. It's now. Hello? 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 Yeah. So. Hey, I spent much more time than I anticipated in the data market. So let's see how far I can get here. And as I told you, that I'm beginning with the very basic concepts and then build up to the modern times. So we are going to do machine learning. Have you connected the USB here? So that's the point. And we'll get on back. Oh. So, let us know first, what do you mean by training? You all been hearing about training and algorithm. I might have any kind of algorithm at all, upper encoder. Okay. So in the most trivial case, you will have a learning algorithm, which in the very early days actually used to be a hardware device. Very complicated hardware device, but not just a computer program. And then you're going to train it. Both are equally important. No training data, no learning. No learning algorithm, no training. So you need both for it. Then, when you successfully finish the training, you get a train model. The models might be performing any particular task there. For a train model, and what you will do with it is that you will test it out. You see how well is the model working. I come and give you a train model, where you can download a train model, and you want to see how well it is working by using test. And then if you like it, then you'll use it to carry your classification on. Now, when it comes to data, there are two main streams of data. One is data with labels. So, for example, if I'm, let us say, trying to learn certain pieces of music, identify certain pieces of music, then what I will do that I'll take a piece of music, an audio track, and to that I'll attach a name, saying that this is from the film Ajit. Right? And then I go on training and then it learn to recognize this. But I may not have other data. So we come across examples of data where there's a lot of data which you want to classify, but you don't have labels. And in which case, you have what is called unsupervised learning. Here you have got supervised learning, and then you have got unsupervised learning. And then there's of course always a bridge between the two. And the auto-editor, for example, there's a semi-supervised learning. So we come to that. So then, how do you input the data? If it is an image classification scheme for that. And so you go to DGR by data in remembering your place. There, you can hardly provide a description of my face in finite number of things. You will give the entire data, the entire image is given there. Well, on the other hand, that is typically what is done in the convolutional neural network. But you can have simpler cases where let us say that I want to distinguish between two kinds of objects, which are pretty simple. That one is a figure of one kind, one is a figure of another kind, which is geometric. Then I can give some properties of the object. So I'll give you an example of that one. Properties of the object are finite number, and those properties of the object are the input data. But that is tricky, meaning how do you say what are the important properties? Are you missing something? What are you doing? But one did that before because of the architectural limitations. Now that we have much better architectures, we can just use the entire original data. That is what the learn has done. So you've got the AI universe, and then you've got machine learning. That you've got what are the examples of machine learning? And ANN, an artificial neural network, or random forest program. So these are all examples of machine learning. But what we typically use now is a subset of machine learning, which is known as deep learning. Deep in the sense that the networks become deeper, there are many layers, and handling them is more difficult. But the applications are many more and complex. So that comes under the deep learning is the more recent thing. And we are going to apply all this to data science. So we'll have different kinds of data, Jim will talk to you about virtual observatory experience of data. And then you want to analyze the data. But one can imagine other situations where data is much more quantitative. Then under deep learning, the two older ones. I told you this is all you are really talking of last 20 years. No more than that. You have got the convolutional neural networks and you have got what are those auto encoders. Auto encoders are extremely interesting and extremely important because they are at the basis of various modern architectures. And then you have got things like recurrent neural networks, which you use, for example, in natural language processing. And so again, again now we have got things like generative, you have got the general space of generating AI. So when you talk to ChatGPT, it is generating an answer. You ask it a question, and it generates an answer. And you ask it to do an image or whatever, it generates it. And the possibility you can use generative adversarial networks for it. Or you can do something like, there are a special kind of auto encoders which can be used for generating data. Then an extremely important techniques and the recent, the more recent ones at the end of the last decade. So then the attention and transformers. Right? The attention mechanism and transformers. Here's one paper on transformers. And the title of the paper is Attention is All You Need. Because previously, in natural language processing, you use recurrent neural networks and attention. And these people invented a technique called transformers. So that paper, there are 8 authors, all of them were in Google, 2 of them are Indian. And then that paper has got 200,000 citations. And this was a year ago, so now they will have many more citations. And it is this paper which is seminally important. And it led to GPT and all the large language models, large multimodal models. The whole thing comes from that one single paper. Then you have got diffusion. Again, that can also be used to generate images. And now we have got the large language models. We are all completely familiar with it, I'm sure you use them all the time. Then you have got the large multimodal models, where the LLMs are mainly based on text. Okay, whereas now you have got text and audio and images or whatever, any kind of data at all. And these are the large multimodal models. And then when you collapse that system, say for example, I'll show you a model with for the sun state, the data solar data. And when you do these astronomical models or models in a particular domain, which are limited, then you have got what is known as the foundation model. So you can use the foundation model to do a lot of different kinds of research. And foundation models are the latest fact. Everybody wants to build a foundation model. The foundation models are cheaper than large language models. Then you have got this very interesting thing called physics influenced neural networks. So I will not be able to touch on that. You see that all these algorithms, what they do is that they've got a loss function. So how do you do the training? You start with basic weights, arbitrary weights, and then you go on, you see how is the performance. Obviously, the performance is going to be bad, but there will be a loss function. And how do you say the bad? Because the loss function will be large. And then, as you proceed with the training, then the loss function becomes less and less and less. And when it goes to a minimum, there is a point you say that the training has been done. So this is entirely dependent on the supervised learning or unsupervised learning. But now there are situations in which it becomes convenient to use the basic physics. And unfortunately, I don't have the time to show you an example. But what do you mean by basic physics? It is supposing you are trying to generate something in quantum mechanics, and then you are training in the test. Then you know that the equation for quantum mechanics is Schrodinger's. So you can put Schrodinger's equation as a constraint of the system. And when you do that, you get a physics influenced neural networks. So these are extremely important. The way you use more and more in doing intricate physical analysis. So I'll just quickly go through this very basic problem. And if you understand this and the next one, you understand it. So what is the problem here? There's a two-dimensional space, x1 and x2. And there are these two sets of points. Each point is associated with x1, x2. That's all. The color and the shape are not important. They are just there for fun. It is position is important. So this is my input data. And what I want to do is a system which will permit me a rule which will permit me that given a new point, you say whether it belongs to this group or that. And so how can I do that? Which I can draw a line like this. And anything to the right of the line is a blue group, anything to the left of the line is a red group. And so now the line is not unique. I mean, I could have put it this way or put it that way. But if you ask a child to do it, first we'll start with the line somewhere here. Then you say it is not good enough, and then you move on. Now the analog of that, finding the correct line, straight line, can be done with what is called as a perceptron. So in our brains, we have neurons, and we have got those all kinds of networks which are there. And you've got a neural network. So these were first inspired by the neural network in the brain. And whatever is called a neuron is called a perceptron. And these are very vague analogy. So what does the perceptron do? The perceptron simply takes in the inputs. So in our case, we have the two inputs. It sums them like this. It multiplies one input by W1, the other input by W2, and it sums it like this. That's what you have here, W dot X plus WC. So instead of two inputs, if I have 90 inputs, then this will be a 90 dimensional ray. And if I want to be, if I put this Y is equal to 0, what do I get? I get a straight line. And so therefore, I can start with arbitrary weights. Then I input 1 point, and I'll say that if this is greater than 0, then it is true. If it is less than 0, it is not true. So, but when I input a point, if it is not true, I change my weights. And I go on doing this again and again and again until I find the correct equation of the line. Once I found the correct equation of the line, it is straight. And what is the algorithm? The algorithm is that if you give me a point x1, x2, I put it in this. If it is greater than 0, it is a blue point. If it is less than 0, it is a red. Right, so my system is straight. So now why do I need to use a perceptron for that? Because you see that people found it very difficult to do all these in the old days. And it was major achievement to show this. Then you understand the beauty of it. Then we go to the next example. So this is what is known as board data. And there's kind of like this. My problem is the same. Either I want to find a rule which allows me to point in the red rule per. So how can I do that? I can draw a curve through those two points. Right? So I want to find an equation of a curve. But you see that the equation of this curve is quite complicated. And what am I going to do? How am I going to try it? In the earlier case, it was obviously a straight line because it was a linear curve. And I could do it easily. Now imagine a situation where I got a 78 dimensional space in which you have got all these points. And I want to pass the surface through that. It's a hypersphere. How can I find the equation? So that is where the beauty of artificial neural networks comes. So what you do then is I take a network like this. So each one of these is a perceptron. But unlike the previous perceptron, which are linear, it gave you W dot X plus W0. It was linear in W and X. Each one of these perceptrons gives you a non-linear output. Right? Why non-linear output? You remember that I need non-linearity to define a curve surface. Then what happens is that this is what's called an artificial neural network. This is the input layer. This is the output layer. Here I get 1 or -1, 1 or 0, depending on how I've written the code. And these are called hidden layers. They're called hidden layers because I'm not interacting. And now here, it is a feed forward network, meaning that every perceptron here, every neuron, you can call it neuron well matter, is connected to every other one in the which comes later. There are no back connections. Those can also be done. For example, in a recurrent neural network, you can have a back connection. Then they are fully connected networks. Okay, meaning that every neuron in any layer is connected to all the neurons in the next layer. Right? So now any statement which you make here, you can have a counter example. When you can design networks in which they can the signal comes back, it's not fully connected, whatever. Then non-linear out. And what you need here is a label data. Label meaning what? For certain values of x1 and x2, I know it belongs to the red, so I say red. But other x1 belongs to blue. Then I need to define the loss function. And then the trade network has to be tested. So, what do we have here? If I take the jth layer, meaning that if I take the first layer, I can have any number of layers. If I take the first layer, for example, I take in the first layer, I got the jth neuron, and you see that it is connected to all of the neurons. So I got for every connection, I got a weight. For every connection, I got a weight. right? And then what I do is that having got this is a linear term. Now having got the linear one, I use a non-linear function. These are very, very simple non-linear functions, which I use here. Then I go to the set. I do that for all the layers. Then I go to the next one and so forth. And then I will use a loss function. I've got the loss function here. Yes. So you see that this is they get to more complex loss functions like entropy, etc. But what do I have here? The true value. True value is either 1 or -1, meaning red or green. And this is the value. I start with arbitrary weights. I put in the value of a point. And then what I will get is a value either 1 or -. So it is either correct or not correct. If it is correct, I go to the next point. If it is not correct, then I change my weight slightly. And this is what in calculus is known as the method of steepest descent. And so I change this weight like this. And then I go on doing this. Again and again, I put the data accurately. And unfortunately, I forgot to put the loss function curve actually. The loss function is going down like this. And then, so you minimize the loss function. When you minimize the loss function, then you do the testing. How do you do the testing? You leave aside the points which you should have done trading. You take a new set of points for which you know the labels. And you see what fraction come out right. If it is a simple problem of this kind, I mean, it will be virtually 100%. Whereas if it is a more complex problem that you're solving, then you get 80% correct is considered to be very good. And then when the first revolutionary neural network was derived, at that time the accuracy went up by 5%. And that was considered to be phenomenal. And those people later on got Turing Awards and Nobel Prizes and so on. So then there is a, now you see, it is simple because here you have got the derivatives. Now, in complex cases, like when Ranjan Gupta very long ago here actually said this problem of spectra. So where they could have 1,000 inputs in the section. Okay, and you've got 1,000 inputs and you have got again hundreds of these layers and the number of weights goes up. So changing WI by hand becomes impossible. And which is why people kind of use layer things. And then people invented a method called back propagation. So there are people who actually invented back propagation, but historically it has been done here and there many times. And back propagation in just 2 cycles allows you to determine all the derivatives. So it is this kind of an invention that makes you progress in neural networks. Right? So you use back propagation, and the technique was a major step in the development to carry out the minimization. Okay, here I want here the non-linear function. You know that it will non-linearity. So this is called a sigmoid function. So as z is equal to, when you go to minus infinity, it goes to 0. When you go to plus infinity, it goes to 1. And it varies very slowly. And the entire variation of the data is captured by just the simple function. There's an even simpler function called prelude. And the definition of the function is given here. What does the definition mean? That for any negative value, it is 0. And for positive value, it is straight line. And it is this part which introduces the nonlinearity. And so when you do all that, and the network was built, so Amit Kumar, the LSC student in Alipur, I'm working very closely with him. So he did this for me. And then you can see the beautiful separation of the points. And this is a very simple network. It took him about 20 minutes to write the code because he used all the existing things. And then, then you see, now understand that this is actually not a curve. In a sense that we don't have an equation for it. We neither have started with the equation nor ended with the equation. What we have started with is an untrained network. What we have ended with is a trained network. And if I give it any point here, it will put it in this region. If I give the x1, x2 values in this region, it will. say there is a point in distribution. So it has divided the space into these two divisions. And this can be done regardless of how many dimensions there are. Now imagine another problem where I got a cluster of points here, cluster of points there, cluster of points there, and I want to learn to distinguish between them. So if you think for a moment, you see that what you're trying to do is to define a function. So here we say I have defined a function. What is that function? F x1, x2. So for x1 and x2 in this part, it has got a value 1. If x1 and x2 in the other part, it has got a value 1. So now if you give me a more complicated division of points, I'll get a more complicated. So then what is the question that you must ask me? Which is the class of functions that I can represent by elements like this? So there is a theorem like which was derived in the 80s. And what it tells you is that regardless of how complex the function is, we can always have a single layer network which allows you to solve the function, to take a classification. But a single layer network is not convenient, so you can have 2 layers, you can have 3 layers. But as you increase the number of layers, you see that to solve a simple problem with 3 layers is quite all right. And the problem is difficult. And then the number of weights keeps going up. And it becomes the training starts taking a long time. So you see, for the large language model, for example, if you read all the amazing kind of news which comes up, then you will see that Microsoft is giving $15 billion to GPT. Okay, what is the GPT company? I've forgotten the name. Okay, so what do you do with $15 billion? I mean, I can't have higher millions. So all that need $15 billion for what we call the compute. In my time, we used to call it computation. Now we call it computing. That's when the compute becomes more and more expensive. So that is why the training company calls it data center in space. You don't know how much of it is nonsense. Just I people that want to go up as fast as possible. But it is true that as the networks become more complicated, it becomes very expensive to run. And so here's an example. You know how this is. And let us say that my example now is to learn to classify such cases. I want to classify human cases. I want to learn to classify all of you. Now, most of you have seen for the first time. A few people here I've seen. So my brain has learned certain faces. We have to learn the other faces. So if I taking a course of 7 or 8 lectures, at the end of it, I'll be able to recognize most of you. So how do I recognize your faces? My brain doesn't make a pixel by pixel analysis. Because if I want to train a neural network with this, you know that this kind of thing can have 10 million pixels over. So it would mean that if I take each pixel, there are 10 billion of them. So I take 10 billion inputs. And there is no way in which you'll be able to run nothing like that. Then you understand that my brain is not doing the pixel by pixel analysis. What my brain is doing is a feature analysis. So it is looking at your face, and it's looking at your eyes, your eyebrows, your hair, your nose, your lips, and there is a particular pattern. And my brain is learning those patterns. And so that is what we want to do. In that we want to learn, take a face or whatever is the input data and break it up into patterns. And simple patterns. And those simple patterns are going to be used in analysis. So how do we do that? Yeah, okay, here's another possibility is that I reduce the resolution. And when I reduce the resolution, then in order to make it, you will not be able to distinguish the face. Like for example, I say, who is this? You say it is Barack Obama. But if I reduce the resolution more and more and more, at some point you will not be able to tell me whether it is Obama or it is Trump. You don't want to reach that kind of a situation. So what you need a different approach. So let me look at this approach here. the bicycle, the image of a bicycle. Now I want to break it up into features. So behind that there's a wall, is a brick wall. And then you will see that the brick wall has got vertical things and horizontal. Right? So the features here are very simple. The bicycle is made up of verticals, horizontals, and diagonals. And then that is not the thing. The seat has got a different texture. The metal has got a different strength. There are all kinds of properties with it. So what we are going to do now is, for example, now this is known as a vertical filter. So what you do is that you have got thing here. I put the vertical filter here and convolve it with the image. What do I mean by convolution? Is that when I put this here, there will be some elements of the image there. And I multiply the element behind this by -1, this by 0, this by 1, and so on. And I'll get a number. Right, so when I pass it like that, then I don't go and input in that number there in that image. But you see that if you actually do the hand calculation yourself, you will find that when I'm passing them, the verticals will give me a residual number. And a horizontal will not give, will give me 0. Very, very simple. So after I've passed the vertical filter there, you see the brick wall, just for the verticals are remain, the horizontals are all disappearing. And here, because they are not all vertical and horizontal, it is that the verticals have become emphasized. For example, the bar here is not there. Then I take a horizontal filter and pass it. Right? So you see here now, the horizontal lines are there. And then here also this is very emphasized now. So the idea is that I take these simple filters and then I pass them across the image. And then I will get these outputs, which tell me that look, these are the vertical filters here. I mean, these are the vertical elements, these are the horizontal elements and so forth. Then you carry on one more very important operation, and which is called pooling. So you see that again, this is my, so you see, I start with this 2 by 2 area. So I'm starting at the left hand corner of the image. And look at the 2 by 2 thing there. And out of the 4 elements, which are like this, I pick up the biggest one. And that is where the max will comes, biggest. Then so I put 5. Then here I get 9, and here I get 12 and so forth. So these 16 numbers have now been reduced to 4 numbers. And the expectation is that these 4 numbers are good representative of those 16 numbers. So instead of taking max, I can take the average, I can take the mean, I can take the median or whatever. Right, so you see that first I have passed it to a filter and then I have max moved it. Now I build up a network. And what the network does is that this is the first convolutional neighbor, meaning that there are maybe there can be 100 filters, different kinds. Then I max moved it. First of all, I have to introduce non-linearity and then I do the pooling. Then I go to the next layer and I go and bring that. So what is happening is that I am reducing a whole set of features, introducing extracting a whole set of features, and then I'm downsizing them. Now, the beautiful thing is that you don't specify the filters. When you build a convolutional neural network, for example, this is called an AlexNet. These are all standard networks. If you want to use AlexNet or there are various other networks. So you don't specify the filters. The filters are learned. Okay, meaning that what you mean by learning is that you tell the network that use 100 filters in the first layer. And the filter should be 3 by 3 in size or 4 by 4 in size. So then what it is doing is that it is trying out different filters and it will see what will give you the best result. What will give the best result is that you eventually will minimize a loss function. Right? So then, what the extremely important thing is that when you have reached this stage, the data has been downsized very much. And what you have got would be called the latent space. When it is the space which has got enough information about the data. The information which it reveals is not important as in thrown. Enough useful information has been collected. The dimensionality is much smaller. And then what you can do is that you can now introduce a ANN, a classification. I told you what's called an ANN. So if you are having billions of pixels of Barack Obama's face, you now have a limited number of naked brains, and you carry out the classification. And when you do that, you get what is known as a convolutional neural network. Right? So you see here, this particular network has been trained to distinguish between those 5 objects. And then here I'm showing you a car, and you see that this bar is the longest, meaning that the probability that that object in the car is the highest. So you have classified it correctly. Right? These things here are all, these are all those filtered, the convolution. After you carry out the convolution, what is the pattern that you see? So I will give you an example very quickly of these layers. Now, machine learning libraries, you have got TensorFlow and Keras. Very vaguely, the difference between them, if this is like tech and this is like that. Okay, so a person first wrote Keras, then they invented TensorFlow, and then he made Keras for TensorFlow. Then you have got PyTorch, which is very popular now. And using all these libraries, if you say that if I ask you to set up a vector, set up a network like that, then you use one of the libraries and you select the kind of architecture you want, and quite quickly you are solved. And so, yeah, I've already said all the things. Now I come to the next very basic kind of architecture, or the kind of, it's not, yes, that we call architecture. So it is called an autoencoder. So what is an autoencoder do? So you see, the first part of it is not an encoding. So I start with an image or a spectrum or whatever, any kind of astronomical data, whatever data. And then what I'm doing is that I'm passing it through something like a CNN. I'm passing it through different layers and reducing the dimension. So to give you an example, supposing I have a spectrum. I told you what the spectrum is, that I have a wavelength against intensity. And how many points do we have in the spectrum? Because let's say I've got a spectrum with 1,000 points. I'll give you an example. Now I take a spectrum like that and input it into the encoder. And it applies all these techniques. And then it reduces the space in the manner that I already described to you. And it makes something called a latent space representation, which also I've already mentioned. So it is possible that I've got 1,000 input points, and the latent space is just 50 points. So I've gone from 1,000 points to 50 points. Then what you do is that this process by which you arrive at latent space is now reversed. And then you get what is known as a decoder. What does the decoder do? It starts the latent space and then it rederives the input spectrum. So I got input spectrum, went to the latent space and come back to the spectrum. In the first pass, I have arbitrary weights. You remember that everything has got the same architecture. There are the weights associated with it. You start with arbitrary weights, and then you put it in, and you will not get the spectrum, you will get some jump. But you keep changing the weights. How can you change the weights? You use backpropagation. Then you change the weights until what you get finally becomes identical, almost identical to your end. So you minimize the thing, you get the. So then you say, what is the point? I mean, I just reduced the latent space and got it back. Now imagine doing that for 10,000 spectra instead of your one spectrum with 10,000 spectra. Each will have its own latent space variables and then you're decoding. And now you train the system so that you get the best results for 10,000. Meaning that those single spectrum will be identical in the input and output. But what will happen is that it will not be identical, but you will get the best solution possible. So let us look at it. What comes next? Yeah, exactly. So this is an actual architecture here. So you see your convolution layers, back pooling, and so forth. You have got to think that good. Now the beauty is that when I'm giving it these 10,000 spectra, those are not labeled spectra. I'm just giving it 10,000 spectra of one kind. That's all. Then you will say, what is the use of this kind of training? After the training is done, I remove the decoder and I replace it by a ANN classifier. Right? And now I train this one on label spectra. And then once it is trained, I can use it to classify spectra. So let us look at an example. And this is probably from London's old paper. So you see that these are stellar spectra, exactly the kind of things I showed you in my first lecture. This is a star spectrum of certain kind, certain kind, certain kind. Now, I have used 50,000 spectra like this to train an autoencoder, meaning encode, decode. And once it is done, look at the latent space. Because here there are about, I don't know how many points are there, maybe several 100,000 points over here. And here we're just 15 points. Right? So now what I do is that I recover the thing, use the decoder, I can recover it. And you see the spectrum that I got now. The noise, you see this thing, rapid thing which you see is the noise, that is gone. But all the important absorption lines are preserved. And so now I can carry out the classification on this one because it's a much simpler thing. I won't carry out the classification, I carry out the classification using the latent space. So these autoencoders are very important, for example, in transformers. I told you transformers is a correct application, and that is where they come. And then there's a variation of this, variation of autoencoders. So what do? See now, when you got the latent space, I said that there are 15 points in the latent space. It's 15, 28, 10, depending upon the case. Now, let's suppose that instead of producing exactly these 50 points, I produce pairs of points. And the pair is what? It is the pair is the maximum, okay, or the mean value, and the other one is the spread of a Gaussian distribution. The mu and sigma of a Gaussian distribution. So instead of having 15 points, I have 30 points. And each point is for the Gaussian distribution. So now, what is the use of this kind of distribution? Either after I done the training, I want to now generate new spectra. So as I told you, we are again generative AI is very, very important. I want to generate new spectra, which are similar but not identical to the spectra that I have used in the training. And so each time I pick a point, what I'm doing is I get a mu and sigma. So I construct that Gaussian and take an arbitrary point from the Gaussian. So if I do this a billion times, I get a billion spectra, which are similar to spectra which have been used in the training. So this is an example of generative AI. So astronomical applications to AI, let me skip this. So galaxy morphology. So this is why I'm showing you this. Because This problem has a long history. I'll come to that. What is the problem? The problem is that this is a field in which there are these objects. If I ask you what is this, you'll say it's a galaxy. But if I ask you what is this, then it could be a star or a very compact galaxy. So how do I distinguish? That's fine, because it is very important. Let us suppose that I want to pick up faint galaxies or I want to pick up very compact galaxies. How do I do that? So, so you see that a star, because of the spreading of the atmosphere, has got a profile like this. It's a two-dimensional Gaussian, and there are complications, but in the simplest, it is two-dimensional Gaussian. You take a Gaussian and you rotate, and that is the intensity distribution of a star. But this is the intensity distribution of a bright galaxy. It goes up like that, and then you got wings. And this one would be a faint galaxy. Right, so what you want to do is to be able to distinguish this one and this one. So long time ago, I think this was in 2002, 24 years ago. And this was probably one of the first applications of machine learning to astronomy. So my friends, Ajit, William, and Yogesh was my student at that time. So we, and Babu Joseph was Sajid Phillips' guy. So you see, what we did was that we took a small number of compact galaxies and a small number of stars. I looked at them very carefully and decided which was the galaxy and which was the star. So from the field that I showed you, you picked up these objects. Having said that this is a star, this is a galaxy, we measured three parameters. Right? Meaning, here goes the central brightness and the way the thing falls off. The three parameters for each galaxy. So this is what is called the data engineering. We are reducing the complicated shape to the three parameters. And then we build a network with three inputs, and the output is again 1 or -1, meaning star or galaxy. And we take, and we got the results, and then we publish it. Now, you see that if I send a paper out for publication like this, I will consider me mad. Because I will get thousands and thousands of galaxies, thousands of stars, and do very complicated analysis. At that time, neither the authors nor the referees were aware of what the real situation was. That's what we published this paper. Then later on, our student, Shiru, was a physics student, and she learned how to distinguish between stars and quasars on the basis of their colors, because they are both very similar objects, they are very compact, but one is bluer than the other. And so you have 5-dimensional color space in which you deal. And in more recent times, when during the COVID time, I gave this problem to 4 interns. 2 of them were from ISO Bhopal, one from Bombay IIT, and one from VIT. And they, because in COVID time, so we never met each other for 2 years. And then the idea was, you take these images of galaxies, a star, and a quasar. Images like this. This is a quasar, this is a star, it's a whole space telescope picture. And then you use, in the old days, you use the ANN, here you use the CNN. Use the images and do the classification. So they built a nice network like this, and a CNN architecture. And then also, I will not go into the details, they use an ANN classifier using data provided by the Sloan survey. And then they got very nice results. Okay, so you see, these are the feature maps, meaning when you apply different filters to different kinds of objects, these are the images that you get, you do the classification. And then when you present the result, have they done a good job? Is it useful? Is it a useful product? So you see that this is known as a confusion matrix. So you take objects which are, you know they are star and you know that they're galaxy, and you predict what they are. So an object is here, would be a galaxy, a true galaxy, predicted to be a galaxy by the network. And here, a true galaxy has been predicted by star, meaning that this is wrong. So you see that along the diagonal, you have got 98% of the diagonal, you have got 2%, which means that in 98% of the cases, you are getting the correct disturbance. So it's a remarkably good network for that purpose. Now you go to more complex network. In that we want to detect bars and rings in galaxy. Right? So what do I mean by that? You see that this particular galaxy is a spiral galaxy. And it has got beautiful spiral arms and a disk and a bulge. Yeah? But this galaxy is different because it has got a linear structure. And this galaxy has also got a linear structure. This galaxy has also got a linear structure. But the linear structures are astrophysically very important. Because if a galaxy develops a structure like that, then stars and gas can go from the outer region to the inner region. And that changes the galaxy, brings about galaxy evolution. So therefore you need to say, if I look at a large number of galaxies, I would like to say how many of those are bars and how many of those are no bars. Or if I go to the next picture, so you see this beautiful faint ring around the galaxy. Here also there's a ring. And here again there's a ring, but there's no ring here. So a small percentage of galaxies have the rings. And my job is to find rings in galaxies. Okay. So I can do that visually, but it will take a long time. Let's suppose my problem is to look at a sample of 1 million galaxies and say which are rings and which are no rings. And then how do I do that? So I take a lot of galaxies, meaning a few thousand galaxies, which have so these are things that neither a ring or a bar, and these galaxies are all of these have bars. You see that in some cases the bars are obvious, in some cases they are not obvious, and all these galaxies have rings. So it was done in 2 steps. We developed the architecture again, used AlexNet. This was done quite long time ago. And then this was our first use of CNN. And we developed this network to distinguish between bar and unbarred galaxies. And then, see again, after different filters, you get these visualization filters. And then you see that the precision and accuracy are very high. I won't have time to define those. And successful network. And here is here's confusion matrix for rings and precision for that. So now, what is the net result of all this? What are the products that we have got for sale here? One is that a network which can find bar galaxies, and another network to find ring galaxies. So now, what happens if I use them in sequence? First, I find bar galaxies, then I pass them through the ring galaxy network, and what will I find? I will find galaxies which are both bars and rings. And there are not too many examples of those known. But we have developed, once you do this, it takes it can take several days for the training. But once you have done that, if you just give me a catalog of 100,000 galaxies, it will take some 10 seconds to go through it. And then we develop these very large samples of bar and ring galaxies. But then, can I extend it further? Meaning that you see that here, there are different kinds of rings. There is one kind of ring, other kind of polar ring, all sorts of different rings. And we are right at the moment learning how to do this. We not only say that there is a ring, but try to say what type of ring. But what happens if you go to this sort of thing, where there are all kinds of complex features. For example, there are dust lanes. So here you have got tidal tails. Meaning what? The 2 galaxies are interacting. And then you see that you get this tail from it. Then you have got these mergers of galaxies. So I want to make an atlas of galaxies where I have large samples of all the different kind of galaxies. The problem is in getting the training data. Everything depends on the training data. And we don't have large samples of training. And then how do you acquire the class samples? You get to stable size. So we had some programs running for 1 million galaxies, at which what happens is that if you register for that, just put 1 million galaxies and you create your village website. If you register for that, then you'll be, when you start the program, you'll be presented with a galaxy. And then there are these questions there. Does it have a spiral? Does it have a bar? Does it have, is it edge on? And there are examples of all this. And then you can say, you just have to type, you have to click either yes or no. Once you do that, then you get another galaxy, you get another galaxy. So if you do this for, let's say, 15 minutes or half an hour per week, you could do 20 or 30 galaxies. And then a very large number of people doing it. But the important question is, if one of you who's completely untrained tells me that these 20 galaxies are bars, how can I have confidence in the result? Because you could simply toss a coin and say that. Right? And then you think to be true only 50%. So how do I get this? The way to do it is to show exactly the same galaxies to a large number of people. Right? When I show it to a large number of people, a large meaning what? So you can work out the statistical distribution. So supposing you said random that it is a spiral or not a spiral. It is like saying at random, it is like heads or tails. I toss a coin, then I get heads or tails. If the coin is a true coin, then I'll get, if I toss it 20 times or 100 times, I'm likely to get 50 times heads and 50 times tails. But it is not exactly, it's a binomial distribution. Right, so what we do for that the same galaxy is shown to about 30. And then the majority say that there is a particular feature, the probability that the answer is correct is like 99%. Right, so it's a very good statistic. So we do that. We are collecting the sample, but there are other people who have done this for decades. Like so there's a galaxy zoo fund that does this kind of thing for decades. How much time? Done? Okay, let me see what comes afterwards. No mass after that.
Not just
No. Oh, let's just look at it as start. So as I said, I mean, if somebody needs me afterwards, I can tell them who's fun. Okay, I will go to, this is an example of a modern thing called explainable AI. Right, meaning after I have trained the thing, then how is the network working? And how do I know it is working correctly? And what is it looking at? And you want to understand that. The example of explainable AI, and after that I will go to generative AI, and after that I will go to what is called the Surya foundation model, which is a foundation model for solar data, which is a model developed by NASA and IBM. So why did they call it Surya? They call it Surya because of the fair number of Indian people there on the team. All right, let's stop it.
We thank Ajit for an excellent talk. I think let's do questions with Biryani, right? Because Biryani is served. So
Okay.
yeah, let's go for dinner. Sorry, we keep
Yeah,
questions at lunch.
No problem.
We should find Ajit there. Proceed for lunch.
Can we leave everything?
Sorry, yeah, I think everything here. And then we continue at Kembhavi. So, right, so please don't wander off. So eat less and come back. We have enough. So food is served outside. I think it'll be okay because I got enough. And then because the LPG problem, people can't go to the guest house. So
Yeah,
food
yeah.
has come here.
Yeah, that's good.
Up to you. Rita,